Hi everybody. Today, as a follow-up to the GPS lock frequency standard project we've been working on, I thought we'd have a look at some improvements and upgrades to this project. Now, following on from a lot of feedback I've been getting on this, I've been looking at ways of improving the ability to switch the output frequency rather than have a simple rotary switch here that switches just a few frequencies. I thought it'd be a good idea if we had the ability to enter a particular frequency via a keypad. But in order to do this, what we have to be able to do is somehow program the GPS module directly via the Arduino on the board here, rather than use the PC at the start of the project to configure the GPS module. Now at this stage I'd like to say a big thank you to one of my regular viewers, Andre Eisenbach, who's helped me in the software for this upgrade, which will allow us to use a keypad entry to program the GPS module directly and give us a particular frequency. Now the intention today is we're going to use a 4x4 matrix keypad, these sort of keypads that you can find, or these membrane keypads which are quite popular these days, very cheap. They've got a self-adhesive pad on the back that you peel off and you can stick it onto a project box. So we'll look at the ability to use either of these particular keypads on this project. So first of all, let's have a look at what we're going to do today. Right, well here we have the changes that we'll make into the project today. The Arduino Nano that's driving the liquid crystal display, that doesn't really change, so the connections to the LCD remain exactly the same as they are on the current project. But what I will be doing is using some of the spare pins on the Arduino Nano to drive both the 4x matrix keypad there and also to send signals to the GPS module to configure it directly. So first of all, the keypad, we're using 8 pins there on the Nano to drive the keypad. I'm using D2 to D5 pins for the rows on the keypad, and I'm using A2, the analog pins A2 to A5, but as digital pins I'm using that to drive the columns of the 4x4 matrix keypad. So that gives us our keypad entry feature there, and I'll cover more details of what the functionality of those keys are shortly. Now the signals going to the GPS module, I'm using A0 and A1, they're 2 other analog pins but we're using them as digital, and that's going to send the information to the GPS module to reconfigure that module to change the frequency. So we're going to change the frequency on the fly. Now you'll notice here I've got a logic level converter there between the Arduino Nano and the GPS module, and the reason behind that is that the GPS module itself, although it's running off our 5V supply, the actual Neo 7 bit in the centre of that module actually is running on 3.3 volts. There is a 3.3 volt regulator on the GPS board, but the output pins from the Neo 7 module in the centre are going directly to the TX and RX pins. And although I found that these can be driven directly from the Arduino Nano, I thought to be on the safe side to prevent any damage, I'll use a logic level shifter there. So the logic level shifter or logic level converter is simply converting the 0 to 5 volt logic signals from the Arduino Nano to 0 to 3.3 volts on the GPS module or vice versa. Now the logic level converter circuitry there, I'm using the 3.3 volt regulated output from the Arduino Nano and the 5 volt output as well to feed that logic level converter circuitry, and I'll cover that in more detail shortly. The other changes that I've made is, if you recall, on the original project we had some noise top and bottom of our square wave, and that noise that we had was caused by the fundamental frequency of the GPS module at 48 megahertz. So what I've done here is I've put a 4700 microhenry inductor there to block that frequency getting back onto the 5 volt line and causing any interference further down the chain. So that's the reason for that. The pulse output from the GPS module is still going to the Schmitt trigger arrangement that we have, and then that's feeding out to an impedance of 50 ohms for our output. Now, since we're making these changes, I thought I'd also use one of the spare pins as well on the Arduino Nano to check the battery voltage. And I'm using A6, analog pin A6, to feed an analog signal to that, which represents the voltage from the 9-volt battery. But obviously the Arduino can only take voltages up to 5 volts, so we have to use a potential divider network here to drop the voltage down suitable for the Arduino Nano. And I decided to use a 47k and a 100k resistor, fairly high, and the reason behind that is to reduce any load that we're putting on the battery. And that's giving us a ratio of 2 to 1. So it's dropping our 9 volts down to a level that can be handled by the Arduino Nano, and then we'll use that voltage and calculate the changes made by the potential divider there to then give us a reading on the display of what the actual battery voltage is. So that's basically the changes that we're making today. And what I've also done is to facilitate all these changes. I decided to have a go at redesigning the display board, and I'll show you that in a second. Here we see the new printed circuit board that I've designed for this upgrade, and what I did also is take the opportunity to try and include as much as possible onto this standard size board. The particular board that I'm using here is a standard size of 100 millimeter by 160 millimeter, so you can get these pre-cut to this size, so that saves a little bit of work. And I've designed it in such a way that it includes not only the display and the keypad, it also includes the Arduino Nano, it includes the GPS module. I've also included the 5-volt regulator power supply on this board, and the little backup battery, a 3-volt battery for the GPS module as well. Now, in addition to that, I also included the Schmitt trigger circuitry on this board as we had a little bit more space. So virtually this particular PCB is in itself a complete project for this GPS frequency standard. You can continue to use the divider board from the original part of the project if you wanted to use that divider network. But I think you'll find that when you look at this, we have all the functionality and we can select any frequency from the keyboard itself. So there we are. I will make this design of this board, the actual artwork for this, available, and I'll put a link below so you can download that. Just quickly going back to the schematic, you'll recall from our original circuit the connection from the frequency from the GPS module to the Schmitt trigger. We had an isolation capacitor there. At that point there we had a 10 nanofarad capacitor giving some DC isolation between the GPS module and the Schmitt trigger. The reason behind that really was because the GPS module itself is effectively running at 3.3 volts, whereas the Schmitt trigger was running at 5, so it's giving some DC isolation protection. But that in itself had some effects, so what I've decided to do is restore a DC level on the other side of that capacitor. So what I've done is I've added 2 resistors. I've got a 10k resistor there going to ground, and at the other side I've got another 10k resistor going to plus 5 volts. So I'm re-establishing a DC voltage level on the other side of that capacitor, halfway between the 0 and the 5 volt supply. Right, well, here we see the circuit of the logic level converter that I'm using today, or the logic level shifter, and we're shifting the logic level from the GPS logic level of 0 to 3.3 volts to the Arduino's 0 to 5 volts, or vice versa. Now this circuit is using 2 FETs, the 2N7000, it's an N-channel MOSFET. One of them is feeding the RX pin of the GPS, and one is feeding the TX pin, and also feeding the A1 and A0 of the Arduino. So in essence both of these halves of the circuit are identical, so let's just focus on this half here to explain how it works. If you look at this circuit, you can see that both the source and the drain of the FET are taken high through 10k resistors. In this case the source is going
to a 3.3 volt supply through that 10k resistor, and the drain is going to a 5 volt supply through a 10k resistor. So in essence you'll end up with a high 5 voltage there on the drain and a high 3.3 volts there on the source. You'll also notice that the gate of the FET is permanently connected to the 3.3 volt supply. So if we look at that, you'll see the source is at 3.3 volt supply, the gate is at 3.3 volt supply, therefore the FET is switched off. If the FET is switched off, then it ensures that the voltage on the drain is held high at the 5 volt supply. So if we now take a situation where the TX pin of the GPS module goes low, it drags the source of the FET low, but the gate is still clamped to 3.3 volts. And what you find now is very rapidly the source to gate voltage of the FET gets to a situation where the FET now turns on. The FET turns on, and effectively you get a short between the source and the drain. So that drags the drain down. So the voltage on the drain is going from a 5 volt down to a logic 0 or a 0 volt. If we then assume that the TX pin on the GPS module goes high, then the source voltage there goes high again up to 3.3 volts. The gate is still held at 3.3 volts, so you have no potential difference between those two, and now the FET turns off. If the FET turns off, it allows the drain of the FET now to rise back up to 5 volts, and that's what's fed to the Arduino. So you can see from that how we can convert the 3.3 volt logic high level from the GPS module to a 5 volt logic high level for the Arduino. If we now look at the reverse situation where, let's assume the signal is coming from the Arduino, so if we assume that the Arduino takes the high voltage there low, it takes the drain there low. If the drain goes low, you'll notice inside the FET you've got a body diode or a substrate diode, and it's taking the cathode of that diode down to ground. As soon as that happens, that diode starts to conduct, and when that diode conducts, it takes the source of the FET low. As soon as it takes the source of the FET low, you exceed now the source gate threshold voltage, and again very quickly the FET turns on. And when the FET turns on again, this time you've got the drain and the source connected to each other, and it takes the source now low to logic 0. So you can see from that, that's how we can convert a logic low going down at the Arduino level, and it's translated to a logic low going out to the GPS module. So this simple little circuit is simply shifting the logic level high voltage from a 3.3 volt high to a 5 volt high. Right, well, just one final point of this circuit is the choice of the N-channel MOSFET here. I've chosen the 2N7000, and the reason I chose that is because of its parameters. You need a MOSFET that has a very low on resistance, so when it's switched on you want the source and the drain resistance to be as low as possible. The other factor you need to consider is the speed at which it can switch on. It needs to respond very, very quickly to the signals. In this case, the switching speed of this MOSFET is only 10 nanoseconds, so exceedingly fast. And the final consideration is the source gate threshold voltage to turn the FET or the MOSFET on. It needs to be low, lower than the 3.3 volts. In our case, this particular MOSFET has a source to gate threshold voltage level of between 0.8 to around 2.1 of a volt. So it's more or less within the range we want. So that's the reason I chose the 2N7000 today. Here you see now I've mounted all the components onto the new printed circuit board, and I'll just highlight the layout. There you can see we've got the Arduino Nano that's soldered onto the board with some standoff pins. Here we have a socket there which is for the GPS module.
and we have some standoffs here which are to support the GPS module. That is the little battery holder for the 3-volt battery backup if we require to use that. There we have the socket for the liquid crystal display, and we have 2 plastic supports there to support the other side. And there's the contrast adjustment for the LCD. Now on either side of the GPS module I've got 2 pins here. I've got a pin there which is the backup supply voltage pin, and I've got another pin on that side there which is the pulse out that goes to the logic circuitry. And in fact on this side here you can now see I've got the Schmidt trigger IC mounted there with its associated resistor network. There's the 2 new resistors I've fitted after the 10 nanofarad capacitor, I mentioned that earlier on, and the output is fed through these 150 ohm resistors to the output pin there, which is the square wave out. On the bottom of the board you can see I've got a socket there which takes the keypad. It'll take the 4x4 keypad, but you'll also notice I've got some pins there which are right angle pins which I'll use if you want to put a membrane keypad, because the pin connection arrangements are slightly different. I'll demonstrate that shortly. On that side of the board we have the 5-volt regulator IC and its associated components, capacitors there, and then this circuitry here is the logic level converter circuitry. There's the 2 MOSFETs, and there's the 4 10k resistors. And finally I've got 2 other little supports here which is for the keypad. Oh, and I forgot that's the 4700 microhenry choke which is feeding the 5-volt supply to the GPS module. So let me now just plug in the keyboard, the LCD and the GPS module, and you'll see how it all fits together. So first of all, the keyboard, I've soldered some straight pins on there, so that will now just plug into there, so I'll just plug that in. And then the GPS module is the little GPS module, so that will now just simply plug in to the socket there. And then finally the liquid crystal display with its inline pins on there, and that now just plugs in onto the socket there. So there we see a completed assembly: display, GPS module, Arduino and keypad. Now if you did want to use one of these membrane keypads, I have on the side there some right angle pins, so basically you would plug your membrane keypad into those pins, and then it falls back, and then that would stick on your project box. So then you wouldn't need that keypad, you'd simply use the membrane keypad instead. So the choice is yours, either the membrane one or the more rigid keypad, which is what I've got here. Right, I think what we'll do now is I just need to solder the pulse out from the GPS module onto the board. There's also the backup battery one, but I'll leave the backup battery just for the moment, just so we can test it. Well, there we have the output signal coming from the GPS module now. I've soldered it onto that pin there on the board, so that's going onto the circuitry there that's feeding the Schmidt trigger. I'll just point out one other thing. You'll notice that I've positioned the Arduino Nano there to the edge of the board, and the reason behind that is I wanted to have easy access for programming, because then we can just put a slot in the project box and it allows us to plug in the lead there that then goes to your PC to program the software into the Arduino. Now I've actually installed the software into the Arduino, so I won't go through that process here today, but I will give you
a download where you can download the software for this project and install it yourself into the Arduino. But for now, let's just unplug the connection. And the first thing I'm going to do is I'm going to connect the power and just take you through the keypad entry procedure. And then once we've done that, I'll then connect the GPS antenna to the unit, and I'll also then show you the results on the oscilloscope and the frequency counter. So let's now connect the battery. The battery pack I'm using here is 6 AA batteries, gives a bit more power. So let me just plug the battery pack on, and you get the startup sequence then on the display. And then the first screen you get is the frequency. It's giving a default frequency there at the moment of 1 million hertz, so that's 1 megahertz. It's shown in hertz as you see on the display. Right, I'll just go through now the sequence of operation on the keypad there. I've got 4 function buttons down the right hand side, A to D. They're the ones we're going to use. And the numerical buttons are just simply to enter in the frequency in hertz. It takes the frequency in hertz. So if I take you through the sequence, to set a new output frequency, this is a lock frequency from the satellite, you press the A button and it then comes up and says set frequency. We can now enter a frequency. Let's say we want to enter 2 megahertz, that's 2 million hertz. And then to send that frequency to the GPS module, you press the B button. And that frequency is now set, so that's now showing you what the set frequency is. The C button on the keypad is simply to check the battery voltage level of the 9-volt battery. So if I press the C button, you get a reading on the display of the battery voltage. These are new batteries at the moment, so it's giving us 9.42 volts. And then to go back to view the current frequency on the display, we press the D button. So that then shows us what the current frequency on the display is. You can then, if you wish, go back and check the battery again at C, press the C, get the battery check, and pressing D goes back to the current frequency set. Now if you wanted now to change that frequency, we can then press the A button again. And let's say I want a frequency now of 1, 2, 3, 4, 5, 6 hertz. And then to send it to the GPS module, you press the B button. And then the frequency is now set. And again, if you check the battery if you wanted to there, and if you want to go back to the display, you can look at the current frequency by pressing the D button. So that's the sequence of the buttons there on the right hand side. We may add some other features later using the star and the hash button, but the software for the moment, that's the features that this particular software is giving us. So the next thing I'm going to do is I'm going to connect the GPS antenna to the module now, and we're going to monitor the output on the oscilloscope and a frequency counter. Right, well, I've got the module now connected to both the oscilloscope and the frequency counter, so we can monitor the frequency accurately and we can look at the shape of the waveform coming out. And at the moment I've disconnected the antenna to the GPS module. So I'm going to connect the battery. What I've done at the moment, I've set the software so with no locked signal on satellite, it'll give a frequency out of around 3.3 kilohertz. So you'll actually see that on the frequency counter and on the oscilloscope. Let me just connect the battery. It's going through its sequence. The default set frequency at the moment for a lock signal is 1 megahertz there, but at the moment you can see that the frequency coming out is only 3.333 kilohertz. And that is the frequency you would get if, let me just alter the scale of that, that's the frequency you would get if there is no lock on a satellite. But that's something we can change later, but for the moment I've just, so we can tell the difference, that's what we have at the moment. So what I'm going to do now is I'm going to connect the antenna. and just see how quickly now it locks on to a satellite. That's locked on pretty quickly there. So you can now immediately see that the frequency is now changed to 1 megahertz. So you've got a 1 megahertz square wave coming out, and the frequency counter is giving us a reading of 1000 kilohertz, which is the same as 1 megahertz. And it's a reasonably clean square wave. We've got a little bit of ringing on the signal there, but maybe that's something we can trim out later. So the next thing I'll do, I'll change the frequency from the 1 megahertz for the moment. Let's say we want a 2 megahertz signal. Remember, we have to put it in hertz, so we press the A button to enter a new frequency. So we now enter 2 0 0 0 0 0 0, so that's 2 megahertz, and you press the B button to send that now to the GPS module, and it's now sent the 2 megahertz signal. So we're now getting 2 megahertz coming out, and you can see here on the oscilloscope we've got a 2 megahertz trace. So let's now put 5 megahertz. Let's try a different frequency. So press the A button again to set the frequency. So we put in 5, 3 zeros, and another 3 zeros. So that's 5 megahertz. Press the B button to send it to the GPS module. And you can see there we've now got 5 megahertz on the frequency counter, and we have 5 megahertz there on the oscilloscope. So let's go all the way up to 10 megahertz now. So let's press the A button again. We now type in 10 and then 3 zeros and 3 zeros. So that's 10 megahertz. And press the B button to send it to the GPS module. And what we've got now is 10 megahertz coming out on the frequency counter there. And there's the 10 megahertz on the oscilloscope. And as we had before, it's not particularly clean at 10 megahertz. That's the sort of shape we've got. But I think we're going to have to work on that. But at least the frequency is accurate, and as a reference you can see that the frequency counter is reading an accurate frequency of 10 megahertz. So let's say we want to change the frequency again, so we press the A button. So let's say we want some odd frequency now, so let's say we want 526 000, that's 526 kilohertz. So send that now to the GPS module, and you can see, turn my oscilloscope frequency range down, so you can see on the frequency counter there now we've got a frequency coming out of 526 kilohertz, and we've got a nice clean square wave on the oscilloscope, and all these frequencies are locked in precisely to the GPS satellite signal. So if we change another frequency, so we check the A button again to set the frequency, and this time I'm going to put in 1, 2, 3, 4, 5, 6, 7, 8. So, and then press the to send that. And in fact, I've actually exceeded what would you normally expect of the GPS module there, but that's giving us a frequency of on the oscilloscope now of 12.3456 megahertz, which is what we've got there on the display. And the waveform is not particularly clean, but it's just showing, I'm just pushing this GPS module a little bit harder. It's not really designed to go higher than around 10, but I found we can go higher than 10 megahertz now, and we're getting a fairly accurate frequency of over 12 megahertz. So let's lower the frequency to 1, 2, 3, 3, 0, 0, 0, and then send that. So that's now reading 1.23 megahertz, and just alter the oscilloscope so we can see the square wave, and there's the square wave out. If you wanted to do the battery check, remember we can press the C button and we get a battery voltage check there. 9.26 volts is the battery check, And to go back to look at the actual reading, we can press the display button D, and that returns the current frequency being generated at the moment. Now what I'm going to do, I'm going to reset the module now back to 10 megahertz, and I just want to check the accuracy of this. So there we've got a frequency now of 10 megahertz, and you'll notice on the frequency counter it's reading 5 zeros, well nearly 6 zeros, and a few digits at the end there. And what I have here on the side here, I have a rubidium frequency standard, which what I'm going to do, I'm going to disconnect the GPS module from the frequency counter, and I'm now going to connect the signal from my 10 megahertz rubidium frequency standard to the frequency counter. So I now have the output coming from my rubidium frequency standard going into the frequency counter, just to check that frequency. So it's reading 10.5014 of a megahertz, so my frequency counter is just a fraction out. So just remember that. And now I'm going to plug in the GPS module again. And the GPS module is just the last few digits there, just a fraction different, but I think you'll agree it's pretty accurate when we compare it with the rubidium frequency standard. So I'm quite happy with that. Right, well I'm going to leave the project there for today. I think you hopefully will agree that this upgrade is probably well worthwhile. It doesn't mean, in this case, making a new printed circuit board, although you could actually modify the existing display board if you wish to add the additional components on there. But what I will do is I'll give you a link down below where you can download the new artwork for the new PCB and also the new schematic diagram with all the changes on. The software I'll give as a link, which will be a zip file, so you can download that zip file, and when you unzip that file, there's actually 3 files within that. There's the main body of the program, then there's 2 other files, which is the library files for the program in the GPS module, but it all comes in one. If you then simply load it into your Arduino IDE software and compile it, it should work fine. But make sure that you're running the latest version of the Arduino IDE. It doesn't seem to compile on the earlier version of the IDE, so make sure you've got the latest version. If I've got the time, I'll try and put together a little document which I'll put in a PDF file and add it below, if not now, at a later date. But if you found this project so far of interest, please give me a thumbs up and subscribe, and I'll see you all again soon next time. Bye for now.